Okay, thank you very much, Andrew and Patrick, for inviting me to give a talk in this seminar. Today, I'll talk about semi-uniform ISS and integral ISS of infinite dimensional systems. Before starting, I apologize to any audience members who may have seen parts of the slides before, because this talk is an extended version of my presentation at MTNS last year. Here is the outline of this talk. First, I'll review the notion of semi-uniform stability of C0 semigroups, and then discuss ISS and integral ISS properties. Let me start by introducing a motivating example of semi-uniform stability. We consider a damped wave equation with direct boundary condition defined on a smooth and bounded spatial domain omega. The wave equation has a damping term here with continuous coefficient A. This coefficient is assumed to be non-negative, which implies that the energy of the solution decreases over time. And it's well known that the rate of energy decay depends on the geometry of the spatial domain omega, and the set where the coefficient A is strictly positive. Physically, this set represents the area where the damping effect occurs. If the so-called geometric control condition is satisfied, the decay occurs at an exponential rate in time. On the other hand, there are various results showing that even when the geometric control condition is not satisfied, the decay still occurs at other rates like polynomial in time or logarithmic in time. Of course, excluding the trivial case when the damping coefficient A is identically 0. Another important point is that these rates are uniform for smooth initial data, not for all initial data. The wave equation presented here is linear, but these authors have shown that wave equations with nonlinear damping or with additional nonlinear term have similar non-exponential stability properties. The stability property discussed earlier can be reformulated using the language of operator semigroups. Let T be a C0 semigroup generated by the operator A. We say that the semigroup T is semi-uniformly stable if it satisfies the following two properties. First, T is uniformly bounded, namely, the norm of T is uniformly bounded over time. Second, there exists a decreasing function MT such that the decay estimate shown here is valid. On the left-hand side, we simply have a trajectory at time t with initial states from the domain of the generator A. And the right-hand side is its upper bound. The function mt decreases to 0 as t goes to infinity and determines the rate of decay. Also, we use the graph norm of the initial state. This estimate shows that the trajectory starting from the unit ball with respect to the graph norm has the uniform decay rate mt. Additionally, suppose that the function m decreases polynomially as in this estimate, where I use the big O notation to describe asymptotic behaviors. As you know, this notation means that mt is upper bounded by a constant multiple of the given function for all sufficiently large t. And if this decay estimate is satisfied, we call the semigroup T is polynomially stable with parameter alpha. Semi-uniform stability can be viewed as an intermediate notion between the well-known concepts of exponential stability and strong stability. To see this, consider a uniformly bounded semigroup T on a Banach space X. As you know, T is exponentially stable if the norm of the trajectory exponentially decreases for all initial states in X. On the other hand, strong stability requires the norm of the trajectory to converge to zero without imposing specific decay rates. Semi-uniform stability ensures a uniform rate of decay for trajectories starting from the domain of the generator. And the decay may occur at any rates, for example, an exponential rate, a polynomial rate, or a logarithmic rate. The point is that for semi-uniform stability, we focus on initial states in the domain of the generator, while exponential stability covers any initial states from the Banach space X. Clearly, exponential stability implies semi-uniform stability. In addition, by the uniform boundedness of the semigroup T and the density argument, semi-uniform stability implies strong stability. In summary, semi-uniform stability lies between exponential stability and strong stability, and it provides a uniform decay rate for trajectories starting from the domain of the generator. The statement on polynomial decay presented earlier has several characterizations. First of all, I introduce the equivalent conditions that will be used in this study. Let T be a uniformly bounded semigroup on a Banach space X, and assume that 0 is in the resolvent set of the generator A. The first statement is the one we use in the definition of polynomial stability, which says that trajectories starting from the generator domain have a uniform polynomial rate of decay. From the definition of the graph norm, we can easily see that it's equivalent to the second statement on the operator norm rather than trajectories. Here, A inverse acts as a smoothing factor for initial states. As the power of the minus A inverse, in this case beta increases, the initial state becomes smoother, which results in faster decay of the trajectory. The third statement here shows this relationship between decay rates and the smoothness of initial states. It emphasizes that faster decay is achieved for smoother initial states. In addition, assume that X is a Hilbert space instead of a general Banach space, and that the generator A is normal with the imaginary axis contained in its resolvent set. Then we can characterize the polynomial rate of decay by the location of the spectrum of A. The location of the spectrum. Here, the spectrum of A. Roughly speaking, the spectrum can asymptotically approach the imaginary axis from the left as in this figure. And the rate of approach of this curve is determined by alpha, the parameter of the polynomial decay. Another characterization has been provided in terms of the resolvent of the generator. It's not used in this study, in this presentation, but I'd like to introduce this famous and beautiful result. In the 90s, Lebowitz shows that the decay rate of damped wave equations can be deduced from the growth rate of the resolvent on the imaginary axis. This resolvent characterization has become well established, particularly for polynomially stable semigroups on Hilbert spaces. Let T be a uniformly bounded semigroup on a Hilbert space X, and assume that the imaginary axis is contained in the resolvent set of the generator A. The first one is a statement equivalent to the polynomial stability, polynomial decay, which I presented in the previous slide. The theorem states that the decay rate of TA inverse can be characterized by the growth rate of the resolvent on the imaginary axis. And in the process of obtaining this equivalence, it's also shown that the third statement is equivalent. It says that the resolvent multiplied by a suitable smoothing factor of the fractional power of the negative generator is bounded on the open right half plane, like the well-known Gerhardt-Prus theorem for exponential stability. In particular, the statement 2 here, resolvent characterization, is often used to obtain the decay rate of PDEs in literature. Additionally, the equivalence between the statements 1 and 2 has been studied in the banana space setting and extended to other rates of decay by these authors. The survey here is also very helpful. Next, I introduce the notion of semi-uniform ISS like semi-group stability, and then characterize it by some attractivity properties as in the uniform ISS case. We consider the following class of semilinear systems. The state space X and the input space U are both banana spaces. The operator A generates a C0 semigroup T on the banana space X. F is a nonlinear map which is defined on X cross U. And finally, the input U, small u, is assumed to be from the L infinity space. But this is just for simplicity, and in the paper, the definition and characterization of semi-uniform ISS are provided for more general spaces. Of course, this semilinear equation doesn't have a solution for every nonlinear map F. Therefore, we assume forward completeness. This property ensures that for all initial states and inputs, the semilinear equation has a unique mild solution. And as in other ISS literature, I use a notation phi of Tx0u to present a mild solution, which helps to clarify the initial state x0 and the input u. Before moving on to the semi-uniform case, I'd like to give a brief overview of two stability notions, uniform global stability and uniform ISS. The system is called uniformly globally stable if there are k-infinity functions gamma and mu such that the norm of the trajectory here can be upper bounded by the sum of these two functions with respect to the initial state and input respectively. This notion of stability doesn't ensure convergence, but boundedness of trajectories. And we say that the system is uniformly ISS if the norm of the trajectory is bounded by a combination of these two functions. The transient behavior is described by the KL function kappa, which depends on the norm of the initial state and time. Additionally, we include the k-infinity function mu, which depends on the input and describes the asymptotic deviation of the trajectory from the origin. Because the first function kappa decays to 0 as the time goes to infinity. Now, I introduce the notion of semi-uniform ISS. We call the system semi-uniformly ISS if it's uniformly globally stable and satisfies the decay estimate shown here. The key distinction from uniform ISS is to take initial states from the domain of the generator and use the graph norm, as in the case of semi-uniformly stable semigroups. We need the property of uniform global stability because the decay estimate here gives no information on stability when the initial state is outside the domain of the generator. In addition, if the KL function kappa decays at a polynomial rate in time for every positive first variable r, as in this estimate, we call the system polynomially ISS with parameter alpha. Okay, you may come up with a question. Is there a nonlinear example which is not uniformly ISS but semi-uniformly or polynomially ISS? One possible example could be a wave equation with nonlinear damping, but its ISS property has not been fully investigated yet, in spite of the recent development of stability analysis of nonlinear damped wave equations. The system here isn't so interesting from the practical point of view, but very simple, a kind of bilinear system. Let A generate a polynomially stable semigroup T with parameter alpha. Then you see that the system may not be uniformly ISS from the zero input case, because the semigroup T isn't necessarily exponentially stable. To make the system polynomially ISS, we next assume that the range of the bounded operator H, H is here, the range of the bounded operator H is contained in the domain of the fractional power of the negative generator. And here, the exponent beta is assumed to be larger than the parameter alpha for polynomial decay. Then the closed graph theorem shows that this operator product is also bounded. Also, the integral term of the mild solution can be bounded by a constant multiple of the infinity norm of the input. The constant C here depends on alpha and beta, but not the time variable small d. As a result, the system is polynomially ISS. It's well known that uniform ISS can be characterized by some attractivity properties. Before introducing the semi-uniform analog, it's useful to recall uniform attractivity properties. Here, we consider two properties called uniform asymptotic gain property and uniform limit property. Roughly speaking, these properties both mean that every trajectory from some bounded region approaches the neighborhood of the origin. We take two positive constants, epsilon and r, and assume that the initial state is bounded by the positive constant r. Then, under the uniform asymptotic gain property, there is a time tau such that the norm of the trajectory is upper bounded any time after the time tau by the sum of the constant epsilon and the under k infinity function mu that depends on the infinity norm of the input. So, as in the left figure, the trajectory doesn't leave a neighborhood of the origin. This is the case of the asymptotic gain property. In contrast, the uniform limit property only means that the trajectory enters the neighborhood by the time tau. So it may leave the neighborhood after the time tau, as shown in the right figure. Clearly, the uniform limit property is weaker than the asymptotic gain property, but it's well known that if the system is uniformly globally stable, these attractivity properties are equivalent. The definitions of semi-uniform attractivity properties are quite similar. The only difference is to use initial states from the domain of the generator and its graph norm, as in the definition of semi-uniform ISS. The rest is exactly the same, so I'd like to go to the characterization of ISS now. The authors here have considered general infinite dimensional systems, not necessarily semilinear systems. and have characterized uniform ISS by uniform global stability and the attractivity properties shown in the previous slide. It's sometimes hard to show the ISS property directly, but it can be relatively easier to show attractivity properties. In such a case, this characterization is useful, so similar characterizations have been obtained for strong ISS and weak ISS as well. As you can easily imagine, the attractivity-based characterization is also true for semi-uniform ISS, which can be proved with modifications related to graph norms. In addition, as a corollary of this result, we can show that for linear systems and standard bilinear systems satisfying this equation, semi-uniform ISS implies strong ISS. But it's still open whether or not this implication is true for general, not necessarily linear and bilinear, general semilinear systems. We can define polynomial integral ISS in the same way. I'll give a sufficient condition for a class of bilinear systems to be polynomially integral ISS. To this end, we begin by recalling the notion of uniform global stability at zero, which means that the norm of the trajectory with no input can be upper bounded by a k-infinity function gamma with respect to the norm of the initial state. And we say that the semilinear system is semi-uniformly integral ISS if it satisfies the following two properties. First, it's uniformly globally stable at zero. Second, the norm of the trajectory is bounded by the sum of the two functions. The KL function kappa uses a graph norm of the initial state like semi-uniform ISS. The input term here is in the same form as in the usual integral ISS. Please note that the estimate here can be applied only to the trajectories with smooth initial states. To ensure the boundedness of trajectories with no input, and starting from outside the generator domain, we need the property of uniform global stability at zero. And in particular, if the KL function kappa decays at a polynomial rate in time, we say that the system is polynomially integral ISS with parameter alpha. We study polynomial integral ISS of bilinear systems that satisfy the assumption in the slide. Under this assumption, a standard argument using the Gromwall inequality and the fixed point theorem shows that there is a unique multiple solution of the bilinear equation. The nonlinear operator f is decomposed into a linear term big C and a bilinear term g of CV. The operator b of the linear term is bounded, and the function g of the bilinear term satisfies the following conditions. First, the function z is 0 when the first variable is also 0. Second, G has a kind of local Lipschitz property with respect to the first variable, such that this implication holds. And the bound here is linear with respect to the norm of V. Finally, when f is a continuous function and g is an L infinity function, the map here is measurable for all terms. Of course, these assumptions are satisfied for a standard bilinear function, such as C times V, where V is a scalar. This result gives a sufficient condition for polynomial integral ISS. Let T be a polynomially stable semigroup with parameter alpha. Suppose that the nonlinear operator f satisfies the assumption discussed in the previous slide. And also, there is a positive constant k such that the norm of the product of the semigroup T and the bilinear term G decays at the same polynomial rate as TA inverse. And the bound on the right-hand side is linear with respect to the norms of C and V. Under these assumptions, the bilinear system is polynomially integral ISS with parameter alpha. And loosely speaking, the inequality here implies that the bilinear term G maps to a smooth element in X. A typical example is when G equals VA inverse C in the single input case. To illustrate how this inequality was derived, I'll provide a sketch of the proof following the trajectory-based approach, as in the case of uniform integral ISS. Since we assume that the semigroup T is polynomially stable, the norms of T and the trajectories starting from the domain of the generator are bounded from above in this way. On the other hand, the state X of the bilinear system is given by the variation of constants formula. Applying the inequalities into that formula, we obtain an upper bound on the norm of X as follows. Next, we introduce the real valued function z, which depends on the norm of X. Then, we can rewrite the estimate of the norm of X as follows in terms of z. The difficulty due to polynomial stability is the rational function in the integral here. But it can be bounded by 1, so we can replace the integrand by a function that doesn't involve the variable t. This step is crucial because the Grunwald inequality cannot be directly applied if the integrand involves the variable t, this variable t. For this reason, we make the decay assumption on the bilinear term. We have still the polynomial here in the second term, but this term doesn't contain the function z, so that's not a problem. Now we have resolved the difficulty due to polynomial stability, and the rest of the proof can be done by using the Grunwald inequality as in the uniform case studied by Mironchenkov and Ito, so I skip it. Finally, we focus on polynomial ISS of linear systems. As you know, a linear system is uniformly, not semi-uniformly, uniformly ISS when the the semigroup is exponentially stable and the input operator is linear and bounded. But we can easily find that a similar fact is not true for polynomial ISS. In other words, even for a polynomially stable semigroup and a linear and bounded input operator, polynomial ISS may not be achieved. Therefore, our aim here is to obtain sharp conditions that ensure polynomial ISS for linear systems. For this linear system, we assume that the operator A generates a C0 semigroup T, and the input operator B is linear and bounded. As in the strong ISS case, we can show that polynomial ISS is equivalent to polynomial stability of the semigroup plus infinite time L infinity admissibility of B. Here, B is called infinite time L infinity admissible if this inequality holds for all L infinity functions U. From this lemma, it's enough to study the admissibility of the input operator B to ensure polynomial ISS. The admissibility property has been extensively studied, but there has been relatively limited research on L infinity admissibility for polynomially stable semigroups. Using that lemma, we can easily show the following simple result. In addition to polynomial stability of the semigroup, if the range of the input operator B is contained in the domain of the fractional power of the negative generator, and if its exponent beta is larger than the parameter alpha for polynomial decay, then the linear system is polynomially ISS with parameter alpha. Let me show you how infinite time L infinity admissibility is obtained. First, polynomial stability is this estimate for some positive constant m. On the other hand, the range condition here and the closed graph theorem shows that the operator product here, this operator product is bounded. Finally, combining these two results, we obtain an upper bound on the norm of the integrand TBU, the integrand TBU. Since the function here on the right-hand side is integrable when beta is larger than alpha, we conclude that the input operator B is L infinity admissible. You can easily find an example where the range condition here doesn't lead to polynomial ISS when beta is smaller than alpha, not beta is larger than alpha. But as in the special case where the generator A is diagonalizable, this sufficient condition is still valid when beta equals alpha. In what follows, we consider linear and diagonalizable system, which can be defined as follows. Let X be now a Hilbert space, and we say that the operator A on X is diagonalizable if it can be represented by a series as shown here, and its domain is given in this way. The angle bracket denotes the inner product on X, and lambda n here are the eigenvalues of A, and assumed not to be dense in the complex plane, which implies that the resultant set is non-empty. Phi n and psi n both form Lee's bases in X and satisfy this equation for biosonality. Here, this delta means Kronecker delta. In the diagonalizable case, we obtain the following result. Let the state space X be a Hilbert space and the input space U be a Banach space. The linear system is polynomially ISS with parameter alpha if the following conditions hold. First, the operator A is diagonalizable, and the semigroup T is polynomially stable with parameter alpha. Second, the input operator B is a finite rank operator and satisfies this range condition. Please note that here we consider the case beta equals alpha, not beta is larger than alpha. Next, I'll explain the reason behind the difference. Specifically, Wise's theorem for the diagonalizable case has a range condition with beta equals alpha rather than beta is larger than alpha. In the proposition of the general case, we have estimated the integral of the norm of TBU. But initially, our goal is to estimate the norm of the integral itself. This compromise makes the sufficient condition slightly conservative. On the other hand, in the diagonalizable case, we use the property of a Lee's basis, where M1 and M2 are some positive constants. From this property, we can estimate the norm of the integral, this one, more directly. To simplify, let's consider the single input case, and let the input operator B be given in this way. Then each term of the series can be upper bounded by using the absolute value of the real parts of the eigenvalues. Since the polynomial stability gives a condition on the location of the spectrum of A, or the location of the eigenvalues of A, we can obtain the estimate here for the reciprocal of the real parts of the eigenvalues. Finally, the range condition can be written as an inequality on the series in the single input case. Substituting the second estimate to the first one here and applying the equivalence in the third step, we conclude that this range condition leads to infinite time L infinity admissibility. It may appear that the difference is small between beta equals alpha and beta is larger than alpha, but it can have some impact in examples where the domain of fractional powers of the negative generator cannot be obtained explicitly. To illustrate this, let me present an example of an Euler-Bernoulli beam with weak damping. The PDE describes the dynamics of a simply supported beam that has a weak damping term and an external input term. Based on the abstract result by Chiru, Papone, Seifert, Stan, Tomilov, when the input is identically zero, the norm of the trajectory starting from a smooth initial state decays at some polynomial rate depending on the function h is here for weak damping. The following are some specific examples to demonstrate this behavior. Let's begin with the case h equals 1 minus zeta, which is the simplest scenario. In this case, classical solutions with no inputs decay at the rate 1 over t, at least 1 over t, which means that the beam equation is polynomially stable with parameter 1. On the other hand, the decay rate becomes slower when h is a higher order polynomial or the characteristic function with irrational number of constant type, which is an irrational number badly approximable by rationals in a certain sense. To apply our result to the beam equation, we have to reformulate it as an abstract first-order equation. To begin, we define the operator a sub 0 as a fourth-order derivative whose domain is also the fourth-order Sobolev space with some boundary conditions. It's known that the operator a sub 0 has a positive self-adjoint square root, which is a negative second-order derivative, and its domain is the intersection of the second-order Sobolev space H2 and the first-order Sobolev space H10. This domain will be used later. And next, we consider the product space X, the domain of the square root cross L2. We define the operator A sub 1. It represents the dynamics without damping or external input. The state X here is given by the position Z and the velocity Z sub t. Also, we define the operators H and B in this way for damping and external input respectively. After these preparations, we can now formulate the beam equation as this abstract first-order equation. Let H be 1 minus zeta as in the previous slide, and define the operator A in this way, which represents the dynamics of the system with weak damping, but not with external input. Then, by the classical result by Xu and Salet, the operator A is diagonalizable, and as shown before, the operator A generates a polynomially stable semigroup with parameter 1. In addition, since the operator H, capital H is bounded, the domain of A coincides with that of A sub 1. As a result, the range of the input operator B is contained in the domain of A if and only if the function small b associated with the external input is in the domain of the square root of A sub 1. which means that the function B is in the intersection of these solved spaces. From the sufficient condition obtained for the diagonalizable case, we can conclude that the weakly damped beam equation is polynomially stable, polynomially ISS with parameter alpha, when the functions h and b are chosen as here. Please note that since we can apply the result for the diagonalizable case, the condition on B here has become so simple. Finally, let's consider how sharp the range condition is. This is the last topic of this presentation. To obtain a necessary and sufficient condition for polynomial ISS, we make the following assumption. First, A is diagonalizable, and the system has only a single input. In particular, suppose that the input operator B is written like this. In addition, when the eigenvalues of A, the red ones, are sufficiently close to the imaginary axis, like in the gray area, their imaginary parts are uniformly separated, as in this figure. Using the characterization of infinite time L-infinity admissibility established by these authors, we can obtain an if and only if condition for polynomial ISS. Here we consider only the polynomial case, but this characterization of admissibility has been proved for strongly stable semigroups. Therefore, similar results are obtained for other rates of decay. The point of this theorem is that instead of the range condition, we use this estimate for admissibility. The definition of phi k, large phi k, capital phi k, looks a bit complicated. So let's consider a simpler situation for the comparison between this if and only if condition and the sufficient condition on the range of B. We assume that the real part of the eigenvalues go to 0, and that the limit property here is satisfied. It means that the eigenvalues, the red ones, approach the imaginary axis and also the boundary due to polynomial decay. Then the necessary and sufficient condition can be written in this way, when phi k is non-zero for all k. On the other hand, the sufficient condition, B in the domain of the fractional power, is given by using the series representation here. From this, you can see that the sufficient condition involves taking the sum over all eigenvalues in the stripe of this figure. On the other hand, the necessary and sufficient condition takes the sup value among the eigenvalues in the stripe. This difference tells us how conservative the sufficient condition is. But please note that the necessary and sufficient condition requires the real basis psi n, the real basis psi n, which is not always easy to obtain. In contrast, the sufficient condition can be checked without the real basis by using the range condition here. In particular, when the exponent alpha, the exponent alpha is an integer, it's easy to check as presented for the beam equation. Now I come to conclusion. In this talk, I've introduced the new notions of semi-uniform and polynomial ISS. I've characterized semi-uniform ISS by attractivity properties and have presented some sufficient conditions for polynomial ISS and integral ISS. However, there remain several open problems concerning semi-uniform and polynomial ISS. For instance, the relationship between semi-uniform ISS and Lyapunov functions remains an open question. So far, all the proofs have been given by the trajectory-based approach. Also, investigating whether a wave equation with nonlinear weak damping has the ISS property or not is an interesting avenue for future research. And throughout this talk, I assumed input operators to be bounded, but unbounded input operators are essential when considering boundary control of PDEs. So the extension to the unbounded input case, of course with some extra assumptions, is a challenging yet important problem. This talk is based on my recent paper published in MCSS. And here is a list of presentation videos on YouTube that cover topics related to semi-uniformly stable semigroups and PDEs. If you have some interest in this field, I encourage you to watch these videos. This concludes my talk. Thank you.